record this. The problem right now is that when I record this, the files are more than 15 megabytes, and I'm working to be able to upload larger files into Zoom. What I may have to do is to make a whole bunch of copies of what we're recording right now, and then edit each copy to where it becomes under the 15 megabyte limit. But I'll work on that to get it to work. Okay, yeah, good. And then just do, once you do your Ka expression, go ahead and do your start change equilibrium table. And
Okay.
yeah, then this is your starting concentration. And whenever it's a weak acid or weak base, we always drop that minus X to make the math easier. And then you just solve for X, which is H plus, take the negative logarithm of that. And because it's a weak acid, you expect an acidic pH, but you don't expect a really acidic pH. So you'd expect something in the neighborhood of like 3 to 6.
Okay.
Your typical
All right.
value. Okay. All right. Any other questions? So I'm going to go ahead, just like on number 2, you have a weak acid. So this is going to be like the question on slide 34, but the question on slide 34 was a KB question. Hello, Ben.
Hello.
So you just have to modify it by using the generic weak acid equilibrium and then the generic weak acid equilibrium constant, and go from there. Other than that, it would be similar to the KB problem on slide 34. So on question 3, there's a couple of, well, again, what I want you to do is to read the question, and one, we know we're in the chapter on acids and bases. So you know it's going to be an acid-base problem, but let's, like I always say in lecture, let's kind of think forward to the final exam. How do we know this is an acid-base problem? Well, we see things like KB, and we see things like pH. Okay, so once we know it's an acid-base problem, what you want to do is you want to see how many chemical compounds are present. And we see there's only one chemical compound present. And when there's one chemical compound present, it's either going to be a strong acid, a strong base, a weak acid, or a weak base. Well, this one tells us that it's a weak base. We know it's not a strong acid. We know it's not a strong base because we've memorized all those. And we also suspect it's not a strong acid or strong base because it doesn't have a very basic or a very acidic pH. So we identify it. So we look at this formula here is the same as this formula here. So this is a weak base. So we're just going to do a generic weak base equilibrium, and then substitute our data into the, substitute the data we get from our start change equilibrium table into our generic weak base equilibrium constant expression. And then that should allow us to solve for the molarity of the weak base. Okay. So this question here is, it's kind of more of a qualitative question, but you need to have some quantitative information. It relates to the information on these two. I think this is my presentation slide, and I think this is an example problem that the textbook provides. So we note here that we have an acid and its conjugate base. We have the base and its conjugate acid. This has one proton. This doesn't have one proton. So acid, base. This has one more proton. This has one less proton. So this side is our conjugate acid and our conjugate base. And so this side of the equation has one acid, the HF. This side of the equation has one acid, the acetic acid. And our rule is we always go away from the stronger acid. So we look up here and we see that the Ka for HF is bigger than the Ka for acetic acid. So that makes this the strong acid. And because this is the strong acid, we move away from it in our equation. Okay. All right. So once again, this question tells us it's an acid base chapter 15, potentially chapter 16 problem. The difference between chapter 15 and 16 is that all of our acid base problems in chapter 15 have just one chemical compound present. If you're looking further ahead into chapter 16, you'll see that in chapter 16, we start having more than one chemical compound present. But once again, because we have one chemical compound present, the first thing we do is we identify what type is it. Is it a strong acid, strong base, weak acid, or weak base? And because we're solving for a Ka, we know it's one of the weak acids or weak bases. Because this is Ha and this is A minus, this is a weak base. So we want to do a weak base equilibrium problem. And again, just use the generic equation. B plus water goes to BH plus and OH minus. Or if you want, you can use A minus plus water goes to HA and OH minus. Your choice on that. Okay. And you need to know that you'll use your start change equilibrium table and your weak base equation and your weak base equilibrium constant expression to get Kb. And then from Kb, solve for Ka. And because it's a weak base, meaning this is a weak acid, we don't expect a very big Ka. Again, we expect a Ka maybe in the neighborhood of 10 to the minus 5 to 10 to the minus 11 would be a typical value for a weak acid, Ka value. All right. I should have put questions 6 and 7 earlier because being able to identify conjugate acid base pairs is crucial to doing all of these questions here above. So maybe the next time I do this, I'll move questions 6 and 7 up. So again, conjugate acid, we just tell ourselves conjugate acid has one more proton. So you just add one proton to that, just add one proton to that. Conjugate bases have one less proton, so just take that proton away and then remember to adjust the charge. And for our purposes, if you want to take one proton away and put C8, put H4, or if you want to take one of these protons away and put H2, that's fine. Yeah, my internet connection is unstable. Yeah, keep getting that message. Okay. All right, so again, I'll probably move question 8 up. So we just count protons. Okay, H2, H. So this is our conjugate acid and its conjugate base, HS and H2S. So this is the conjugate acid, this is the conjugate base. Okay. So question 9, this tells us that it's a acid base problem. This tells us that it's going to be something about a weak acid. This tells it it's a weak acid. And we see that there's only one compound present. So that says just do a standard weak acid equilibrium, step 1, 2, 3, 4, 5, start change equilibrium table problem. And then use the information given to eliminate some of the variables. Okay, so that'll be similar to that question. On question 10, the reason why I put this one here in is just to emphasize that chemical formulas can get more complicated, but we always look for relationships. Okay, we see here that this is a weak base, and then we count protons. We got 3, 4, 5, and we look over here and we note that we've got 6. So that makes this the weak base, that makes this the weak acid. So once you identify this as a weak acid, forget its formula. Use the generic equation. So we're going to represent this as HA, and we're going to represent this as A minus. Use the generic equation. Okay. The only time you really need to know the exact formulas is if you're doing some type of, I need to know molarity, and if I know molarity in liters, I can get moles. And if I know moles, I can get grams, and then I can go to the balance and weigh it out. That's kind of like what I've asked you to do. Some of you were working ahead on the buffer lab. That's what you're going to need to do in the buffer lab. But this one here doesn't ask you for any information about grams. So just use the generic formula. We've got 5 protons, 6 protons, conjugate base, conjugate acid, weak base, weak acid. So a generic, general, weak acid equilibrium problem. All right. And so this problem is basically the same thing. Let me see, is anybody else wanting in? No, okay. It's an acid-base problem. There's only one chemical compound. We're given Ka. This has 1 proton. This doesn't have 1 proton. So if this is our weak acid, NO2 minus is our weak base. And so just represent this by the generic weak base equilibrium process. At this point, we can forget the formula, and we're just going to represent this as B. So B plus water goes to BH plus and OH minus. We don't have to pay attention to sodium plus because it comes from a strong base, and therefore sodium plus is a lousy acid. We can just cross it out and not pay any attention to it. Excuse me. So once again, we notice that this is a weak base, so we're going to need to know Kb. But we remember that if we know Ka, we can get Kb. And because this is a weak base, our start change equilibrium table, we're going to solve for OH minus, use it to get POH, and then use POH to get our final answer of pH plus. So it's an acid-base problem. There's only one chemical compound present, and you know it's a weak base. So we're just going to do a standard weak base equilibrium problem. Okay. When you do the start change equilibrium table, you're going to find out that you still have too many variables. And so we have to make use of the remaining information to eliminate some of those variables. Well, if we know pH, we can get POH. And if we know POH, we can get OH minus, which allows us then to eliminate some of the variables and then solve for the variable that we're missing.
Okay.
Yeah. So I think what I'll do is I'm going to go ahead and kind of close on that one. And then chapter 16. Oh, that's the presentation. That's not what I want. I want the
chapter 16 assignment is we're opening.
Yeah, I'm going to pop it open here on the screen right now. And I think I'll just do the same audio, same kind of talk you through some problems. Chapter 16 problems. Okay. No one else is showing up. Okay. All right. So the big difference in between chapter 15 and 16, as I mentioned before, is that they're all acid-base. Well, this first part of chapter 16 is all acid-base chemistry. That changes near the end. But in the acid-base chemistry of chapter 16, we have more than one chemical compound present. So basically what that's going to mean is that when we do a start change equilibrium table, we're going to have two quantities that we start with. Whereas in the previous chapter, we only ever had one. The other thing that means is that sometimes the two things that we're going to be adding together, or the three things that we're going to be adding together, actually react with each other. Okay. So we look at this problem. Again, we know it's an acid-base problem, but we note that we have one compound here and we have a second compound here. So it's not a chapter 15 problem. Okay. Now then, what we have to do is identify the relationship between the two compounds. Okay. We note that this is a strong acid, and then we note that we have a base. Okay. Well, bases react with strong acids, so I can actually do that. So we have our generic equation, base plus strong acid. I didn't know why I didn't think of this before. Reacts to form the conjugate acid. And we need to do this always in units of moles. And so instead of a start change equilibrium table, we're going to do a start, react, left table. So we'd start with some weak base. So we're going to need to use the volume and the molarity to get the moles. We'd have to use the, okay. Well, the first question is we don't have any H, so I got ahead of myself. So I'm going to cut that, and I'm going to paste it down here. Okay. So the first question is we haven't even started our titration. So in fact, all we do have is our weak base. And so this is really a chapter 15 problem that we just looked at an example of. Okay. So I can put that in. So just a basic KB problem. And that's kind of what I've got written up there also, chapter 15.
Dr. Sela?
Yeah.
Preston asked in chat, he said you're recording this, so we'll be able to go back and watch you go through this again?
Yes. Like I said, what I'll probably have to do is to break it up into several files so I can upload them onto YouTube. I may be able to get larger files to go onto YouTube. I was working on that yesterday, and I think there's a way to do that. But still, some of these files may even go beyond that larger limit, and if need be, I'll just make several copies, and put the first 20 minutes on file 1, put the second 20 minutes on file 2. And hopefully that'll help all of you. Yeah.
Thank you.
Yeah. Okay. So now then, in this one now is we have our original weak base, and now then we've added the second thing to it, and we notice that the second thing is our strong acid. So the weak base is going to react with the strong acid to make its conjugate. And so since the reaction's taking place, we do it in units of moles. Basically, it's a limiting reactant problem that you learned about back in 151. So we use the volume and molarity to get our starting moles. Then we identify which of these two is our limiting reactant. And if this is our limiting reactant, that's the amount that reacts. It all gets used up. It uses up an equal amount of this and makes an equal amount of this because there's a 1-to-1-to-1 ratio. And then we see what we're left over with. And we should find on this one that we're left over with some base and its conjugate acid. We're left over with two things. So you always focus on what you're left over with. Okay? If you're left over with two things and they're a base and its conjugate acid, we do one of the Henderson-Hasselbalch. So I think on this one you're left over with B and BH plus. You're left over with a buffer to do a Henderson-Hasselbalch problem on that. Again, it'll be just like the example there on slide 56. And on this one, we're going to do exactly the same thing. We'll do exactly the same thing. But now then, since, so the amount of base doesn't change, but now then we've added more acid. Okay? And what we're going to find out on this one is that we're at the equivalence point, meaning that the moles of base that we had to begin with is now equal to the moles of acid. So they're both completely used up. So we're left with no weak base, we're left with no strong acid, and all we have is our weak acid. We're going to be left only with BH plus, okay? So when you're left with only the weak acid, we do a Ka problem from chapter 15. But we have to note that our Ka problems from chapter 15 are in molarity, whereas this is in moles. So we can't take the number that we get from right there and put it directly into our Ka problem. So we have to take the moles that we're left with and divide by the total volume. So we'd add this volume to the original volume here. So take the moles that we're left with, divide by the total volume to get the molarity that we use in our weak acid problem from chapter 15. Right. On this one, again, you're going to do the same thing. Except now then on this one, what you're going to find out is that you're left with some H plus and the BH plus that you've made. Okay. So you think about this, this is a strong acid. And because this is a weak base, this is a weak acid. So forget the BH plus. Okay. Because a weak acid isn't really going to do much of anything compared to the strong acid. So what we do is we just get molarity H plus, and I get pH. We have to keep track of the units. This is all about keeping track of the units. When we switch from, this is in moles, but the rest of our calculations tend to be in molarity. So we take the moles that we're left with and we divide by the total volume at this point. We don't divide by 200. We don't divide by the original 150. We divide by the total volume, the two of those added together. Okay, all right. So on question 2, we again know that it's an acid base problem.
Oh,
We
I have
see,
a quick question.
yeah, go ahead, Ben.
So the total volume of those added together, you're saying like the 150 from the original part of question one, and then just the 100 or I'm sorry, the 200, or also adding together the 145 and the 90 from the other.
Well, no, just pretend, imagine, because you've done a lot of you've done too many titrations in lab. As you're adding the volume, it just continually grows in the beaker you're adding to, doesn't it?
Right.
So we just take what we started with plus what we've added to it at that point.
Okay, so we started with 150, and then I'm saying, are we, like for this particular question, is it 150 plus 90 plus 145 plus 200?
No, no. So this is so this would be like at this point of the titration, we've added 90. And then we keep on adding from our burette till we've added a total of 145. And then we keep on adding.
So that's the total. So at that point, we've added enough to get 200.
Yeah. Mm-hmm. So we take this 200 plus the original 140, 150 for this calculation. For this calculation, we take the 145 at this point plus the original 150.
Okay, so not every single one, just the two were like
it's a running volume. So just the same way you would measure it you remember when you did the KA lab?
Yeah, vaguely.
It's been a while ago, hasn't it? I understand. But you just plotted, when you plotted the data, you just plotted a running total on the x-axis. You know, you started at 0 and then you added 1, you added a second one, you added a third one. So you just continually plotted the running volume. So that's what you're doing
Right.
here. Yeah.
Okay.
So at this point, you've added 0. At this point, you've added 90. So the total volume at this point would be 240. At this point, you've added 145. So if I do my math right, the total volume at this point would be 295. And now then at this point, the total volume would be 350.
Okay.
All right.
Gotcha.
Good. Okay. And so this one's basically the same thing, but now then we've reversed it. Instead of this one, we're titrating a weak base with a strong acid. This time we're titrating a weak acid with a strong base. Okay. So here then we would need just a switch. So again, before any strong acid, this is just going to be a KA chapter 15 problem, because we haven't added any of our second component. Now then on this one, it's the reverse of question number 1. So now then we have our weak acid is reacting with our strong base to give the conjugate base plus water. And we don't care about water. So what I could do is I just put that X through there because we don't care about water. And then we do our start, react, left problem. And what you'll see is that this one here corresponds to the second one up here. Okay. So this one here, you're going to be left with, at this point, you're going to be left with a buffer to do an HH problem. Okay. And then you proceed on the same way. We'd use the same equation. And at this point, we're going to see that we're at the equivalence point. But we started with a weak acid, so at the equivalence point, we have a weak base. So we're going to do a KB problem. Okay. We're going to do a KB problem. We're going to remember to convert moles to molarity. And then we're probably going to have to use Ka to get KB. Because we can look up, we're given Ka, we're not given Kb. But from Ka, we can get the Kb that we need down here, as we saw in chapter 15. Okay. So it's just like the previous question 1, except now then we've reversed the titration. Question 1 was a base plus an acid. Question 2 is an acid plus a base. But other than that, the process is pretty much the same. So here on this one, when we do our start reaction left, we're going to find that we're left with OH minus and A minus. So we forget the A minus, it's a weak base. You get the molarity of the OH minus, use that to get POH, and then from POH get the pH that the question's asking for. Okay. So question 1 and 2 are very, very similar. It's just the equation has flipped around. Okay. So this question, as some of you have been working on the buffer lab, this question is very similar to the first question in the buffer lab. So we have a buffer. And so we've got 2 chemical compounds. This chemical compound, this chemical compound. We know it's an acid base. So when we have 2 chemical compounds, see if they have any relationship. That's not a strong acid. That's not a strong base. That's not a strong acid. That's not a strong base. And then we count protons. This has 4 protons. This has 3 protons. So that makes this weak acid. And that makes this weak base. Okay. And it's a buffer. So what we're going to do is we're just going to use, come on, there we go. We're just going to use the Henderson-Hasselbalch equation. And we're just going to sub in data. Okay. So we know from question 2, we know what Ka is for this particular acid. This particular acid is well, no, we don't know it from question 1 or 2. We saw that particular acid in I think the chapter 15 homework assignment, or you could also just Google. I can spell Google. Google KH. Google Ka for the acid, and you should find that it's 1.8 times 10 to the minus 5. And so we've got our Henderson-Hasselbalch equation. From Ka, we can get pKa. We know what the pH is. We can substitute it in. We know what the concentration of the weak acid component is. And so we can just get our calculator out at that point and determine the concentration of the weak base that we need. We can double check ourselves. I'm going to go ahead and type this in. We're going to find that the pKa is 4.74. Okay. Notice how the pH that we want is more acidic than this pKa. What that says is, so if I put that in here, notice how the 4.5 is less than the 4.74. that tells us we need less base than acid because we're a more acidic pH. So when you do the math, you should come up with a smaller value than 2.5. So you can kind of double check that you're going in the right direction. If we just think a little bit about down here, this is more acidic, which means we need more acid, which means we need less base. So more acid, 2.5, less base would be something less than 2.5. So you can double check that you've done the math right on that. The books don't generally go into that simple way to double check. So now then, the rest of it then is like if you were actually doing this in the laboratory. Now that in this part of the question, we solve for molarity of base. Well, if we know molarity of the base, if we know the liters of the solution, we just remember molarity times liters equals moles, and moles times molar mass gives us the mass of this that we would need to then go weigh out. This is actually, I really was excited about doing this lab for the first time at Red Mountain, so I was kind of bummed that we don't get to do it in person. Because what I would do at this point is, if you were in lab, is you do all the calculations, and then I would actually have you make up the buffer yourself. And then with one of our pH meters, I'd have you measure the pH of your buffer and see how well it came out to being what we wanted it to be initially. Okay? And typically, if the pH meters have been calibrated properly, when you were to carry this out in the laboratory, you come pretty close to your desired pH of 4.5. But we can't do that, unfortunately. Sorry about that. Okay. So in question here, we have a buffer. And again, it tells us we have a buffer, but let's just double check that I'm not lying to you. We have two chemical compounds, and we note this has 4 protons, this has 3 protons, this is our acid, and it's not a strong acid we memorized, so that makes it a weak acid, and that makes this its conjugate weak base. And we know that to have a buffer, we need a weak acid and a weak base. So I'm not lying to you, this is a buffer.
I have a question.
Sure.
If it says buffer, is that one of the key words to note that it's a chapter 16, or is it more of a general thing?
No, buffer is bang, chapter 16. You're absolutely correct.
Oh, okay, thank you.
No, it's a good point. Everybody hear Andy on that? If it says buffer, it's chapter 16 immediately. Because again, a buffer requires 2 things. If we only have one thing, we're back in chapter 15. So as soon as we see 2 things and it's an acid-base problem, we know that we're in chapter 16. And then we identify it like in this question. These 2 things are a weak acid and a weak base, which is what we need to have a buffer. Okay. So I could ask this question. You have 500 mils of a solution containing this and this. What is the pH? I would just leave the reference to buffer out of that question, and you could still answer it by identifying that these 2, weak acid, weak base, comprise a buffer. So we're just going to do it like it says there on slide 11. You're just going to do an HH problem, Henderson-Hasselbalch problem. Okay. So now then, we're going to take our buffer and we're going to add some sodium hydroxide to it. So the main thing on this one is we have to look at that slide 15. I think it's slide 15. We have to figure out what buffer generic reaction That's really the main thing in this one. And we note that we're adding the strong base. Well, the strong base is going to react with the acid part of our buffer. So that says we're going to take the weak acid part of our buffer. We're going to add the strong base. And then the weak acid part of our buffer turns into its weak base conjugate. And then, of course, we make some water. And as we did before, we don't care about the water. So what I'll do on my screen to emphasize we don't care about the water, we'll just eliminate it. And tab, that's what I want. Okay. And because there's a reaction taking place, we would need to do a start, react, left over. Let me put it over here. We'd have to do this all in moles. Okay. And so what we want to do at this point, and again, this will be a limiting reactant type problem, just like it was on questions 1 and 2. You know, we identified what the limiting reactant was, and we used that to figure out what we're left over with. So this is going to be the same way. Okay.
Dr. Sela, this is Heather. And this is the exact same one that I've been asking you the questions about for lab.
Mm-hmm. Yes, it is.
Okay.
Yeah. Mm-hmm. Yeah, so there's actually a lot of relationship between the buffer lab. You know, if we had lab, I would not teach any of these buffer type problems in lecture. Because I think the best way to actually learn buffer problems is you actually make the buffer yourself. And as I did, you know, like I just said back to Ben, you would make the buffer yourself, and then you'd measure its pH to see how well it worked. And then you would take your actual buffer that you just made, and then you would do this to it. And you do the calculation to see what the expected pH would be. And then you do the reaction, you know, you'd add that to it, and then you get the pH meter out, and you'd measure the pH after you've done this addition to your buffer. But because we're not doing lab, I've added it both in lab and in lecture. I know you're not in the lecture part, Heather. Just because I think this is one of the more difficult topics in 152. These acid-base titration problems and buffer reaction problems. So I'm hitting you both in lab and in lecture. Well, yeah, Heather, you're in, yeah. Okay. So I think on this one, what you're going to find out is that you're left with HA and A minus. So that says you're left with a buffer to do a Henderson-Hasselbalch problem. Okay, so just substitute the quantities in to the same equation that you did here. You'll just have different amounts. You'll just have different numbers. Now, when we get an answer for this one, compare the answer for this problem to the answer for this problem, okay? We added a base. So when you add a base, you expect the pH to increase. So we would expect this pH to be bigger. Than a previous pH. Because when you add a base, pHs get bigger. They get more basic. So we can again kind of have a way to double check that we set things up and that we've done the calculation on our calculators, et cetera, correctly. Okay. And after 1.5. So again, so what we're going to, okay. So this time then we're taking our buffer. we're taking the same buffer, and now then instead of adding a strong base to it, we're going to take that same buffer and we're going to add a strong acid to it. So basically, we use the other buffer reaction. So now then the strong acid that we've added is going to react with the base part of our buffer to form the conjugate acid part of our buffer. So once again, we're going to use this equation, copy. Let me give myself some edit, paste. And we're going to do another start, react, and see what we're left with, and then go from there. Okay. If we're left with our base and the conjugate, because this is all used up, it's going to be a buffer problem by Henderson-Hasselbalch. So it should look just like the example that's on slide 15. But again, we're using the other equation because we're adding a strong acid to our buffer. So we need to use the strong acid reaction of our buffer.
I'm sorry, I have a question really quick about that.
Sure.
So just to check, how do you know that it's a buffer problem if the H has been used up and you're left with just the B and the BH?
Well, to begin with, it's a buffer problem because we're adding something to the buffer. So to start with, it's a buffer. Okay. So what you're left with, like in this question, I think this one here, you're going to be left with some acid, conjugate base. And so you're still left with a buffer.
Oh, okay.
But sometimes if the moles of this is equal to the moles of this, you're not going to be left with any of this. You're not going to be left with any of this. You're only left with this. And so that makes it a weak base problem from chapter 15. Okay. Sometimes, if I switch down to this one, sometimes we add more of this than we have this. And so we end up with excess this. Okay. So when we end up with excess this, that becomes exactly like what you did here in questions 1 and 2, when you were left with excess strong acid or strong base. We just take what the excess strong acid or strong base that we're left with, convert it into molarity, get POH or POH accordingly. So there's a lot of similarity between a reaction of a buffer and an acid-base titration. So spend some time looking at how, when you're beyond the equivalence point in your titration, that's the same thing as having added too much of your strong component in a buffer reaction. Okay. In a buffer reaction, where you're still left with the buffer, is very similar or is similar to when you're doing a titration and you're at the point of the titration we called in the laboratory area 2, where you're left with the buffer. So there's a lot of similarity. They start out a little bit different, but you can be left with the same thing. In a titration, you can be left with the buffer. In a buffer reaction, you can be left with the buffer. In a titration, you can be left with just one component and you're at the equivalence point. In a buffer, you can be left with just one component. And in a titration, you can be left with excess component. And in a reaction of a buffer, you can be left with excess component. So if you focus in on what you're left with, you'll see there's a lot of similarity between doing an acid-base titration and doing a reaction of a buffer. So what I want you to do is to convince yourself that they're not totally separate problems, that they start a little bit different, but you're really only left with either in an acid-base titration or a buffer problem, you're only either left with three possibilities. You're left with a buffer, you're left with only one thing, the weak conjugate, or you're left with one thing, some of the excess strong component. Those are the only three possibilities, whether you're doing a titration or whether you're doing a reaction of a buffer. So that's why I give you so many problems to work on, is hopefully you'll realize that and then say, hey, there's actually not as many problems as it looks like, because they start out a little bit differently, but there's only three ways for them to finish. So that's why I'm having you do a lot of problems, is I hope you get to that point where you see just what I said. Okay, so we see in number 5, this is really a chapter 15 problem. You should be asking yourself, why is it a chapter 15 problem? Because there's only one thing present, okay? HCl. But now then we note this is not an equilibrium problem, because HCl is strong acid. So to get the pH, we just need to take the negative log of 0.2. Okay. Now then, we're going to add some strong base to it. And so we go in here and we would use our generic strong acid plus strong base goes to water. And we would do a start, react, left, in units of moles. And now then, this is going to be, if we're at the equivalence point, well, we know the equivalence point is going to be a pH 7. Because all we have is water. Or we're left with strong acid. Well, that's just like if we were left with strong acid in these equations. Or we're left with strong base, but that's just like if we were left with strong base in the previous problems. So once again, we start out and it looks a little bit different. We're using a different equation. But by the time we finish and look at what we're left with the same things. And in fact, this one is easier, because if all we're left with is water, we can say immediately the pH is 7. So this one in that regard is a little bit easier. But the other but the other way is going to just be similar to one of the problems up above, where we were left with a strong acid or a strong base. So we take our moles of what we're left with, and we would divide by the total volume. So in this case, we divide by the 200 mils plus the 200 mils. We divide by our total volume at this point of 400 mils. Okay, now question 6, we switch away from acid-base problems to KSP problems. And you've already done ones like this when you were doing the chapter 14, 15, 16 problems. I think I'm going to skip question 6. Okay, the first part of it. Okay. Now then, in chapter 16, we not only start with some solid that we're going to dissolve, but we start with a solution that contains one of the ions. And now then we're asking for the molar solubility. This is going to look just like slide 54. So we're going to have our lead iodide, if I can hit the right key, in equilibrium with lead 2 plus and 2 chlorides. And again, because this is an equilibrium, this is going to go back to molarity. So start, if I can spell it. So we're going to start with some of this, but we're also going to start with some of that. And none of that. Okay. The problem could have said 0.01 molar sodium chloride. And in that case, we'd start with some chloride and we wouldn't have any lead. But we do the same thing now. We change equilibrium. And it actually becomes easier. So some of our lead iodide is going to dissolve. It's going to give us the same amount of lead because the 1-to-1 ratio. And then it's going to give us twice as much chloride. So we're going to have, and then again, we don't care about that because we don't put it into our KSP expression. So we're going to have 0.1 plus x. Over here, we're going to have 2x, but 0.1 plus x, we're going to say is similar to 0.1. Because we expect, well, we don't expect, we know the KSP is very small. So just like a weak acid or weak base problem, we don't expect this reaction to go forward very small. So the amount that it goes forward is going to be small compared to what was already there. So we can just get rid of that. And then that makes the math a little bit easier. Okay. All right. Question 7 is a qualitative question, relates to slide 88. What we need to note here is that carbonate comes from carbonic acid, which is a weak acid. Therefore, carbonate is a base, and bases react with acids. Okay. So if we add a strong acid, it's going to eliminate some of the carbonate. And according to Le Chatelier's equation, Le Chatelier's principle, that's going to drive the reaction towards the decrease, and our lead carbonate will become more soluble. Have you ever done seen the tests for determining whether a rock is a carbonate-based rock? Have you seen those tests where you take like hydrochloric acid or nitric acid and add onto a rock and see if it bubbles? Well, that's exactly what you're doing, is you're causing the rock to dissolve because you're removing the carbonate. Or the other example of that, the other unfortunate example of that, is all of these old ancient limestone statues are being dissolved because of the acid rain that's raining on them. That's an example of Le Chatelier's principle. The acid in the acid rain is removing the carbonate, causing the carbonate solid to dissolve. Okay. Question 8, you know it's an acid-base problem, but you don't know whether it's chapter 15 or 16 yet, so count how many compounds you got present. We got 1, 2, 3. Whenever you have 3 compounds present, it's automatically a reaction of a buffer. So what you want to identify is it a reaction with a strong acid or is it a reaction with a strong base? And we see that it's a reaction of a strong acid. So at that point, we want to go immediately to our buffer reacting with a strong acid. And do a start, react, left, in units of moles. Okay. And as we saw before, what we're left with is either going to be a buffer. You're going to be left with this, and that's all gone. You'll do a Henderson-Hasselbalch. You're only going to be left with this. So you do a Ka problem, or you're going to be left with this, and you'll just convert this into molarity and get the pH. So the problem may look a little bit different, but again, the reason why I put this one in there later on in the problem set is problems can look different when they start, but they're going to look a lot similar when you look at what you're left with. So that's why I put this one here in there. Again, just to remind you or have a way to help remind you that they can look different, you know, different sentence structure, different words, etc. But beyond that, they're not all that different, especially when you focus on what you're left with. If it's a buffer problem, if it's a reaction of a buffer, there's only 3 things. You're going to be left with a buffer, a Henderson-Hasselbalch. You're going to be left with your weak acid component only, do a Ka problem, or you're going to be left with strong acid, do a convert to molarity and get pH. So problem 9 is basically the same thing as problem 8, except in problem 8, we had a buffer and a strong base. We had a buffer and a strong acid. Okay. Well, here, no, this isn't a buffer problem. We know it's an acid-base problem, but we see there's only 2 things present. Okay. Now, the reason why I put this one in here is you probably have never heard of that. And that's exactly why I put it there. Okay. But when we have 2 things present and it's an acid-base problem, we know, admit, Seth, okay. We know that it's when there's an acid-base problem and there's 2 things present, we know that it's either going to be a strong acid or strong base. Well, that is a strong base, but that's not one of our strong acids. And because this is a strong base, our only other possibility is for this to be a weak acid. And we know it's a weak acid because we've got Ka. So this is going to be a weak acid plus a strong base titration. Which we will do in units of. So we'll do a start, react, left, in units of moles. And once again, it looks a little bit different, but by the time you get to what you're left with, you're either going to be left with a buffer, you're either going to be left with the conjugate weak base, or you're only going to be left with the strong base. So again, it starts out looking a little bit different, but it's going to be finishing the same 3 possible ways. A buffer, because you got these 2 things, a weak base because all you have is this, or a strong base because you have some of this extra. Okay. All right, yeah, so question 10 is the reverse kind of question 9. It's an acid-base problem. There's 1, 2 things present. We recognize this is one of our strong acids, and we know that this is a weak base because we have this KB. So now then, this is just a base reacting with a strong acid. To give its conjugate. So we're going to do a start, react, left, in units of moles. And the same 3 things are going to happen. We're going to be left with the base and some acid, and it's a buffer. We're going to be left with only the weak acid, and it'll be a Ka problem. Or we'll be left with some of this, and we just get its molarity and get our pH. So again, I provided this just to emphasize that the problems can look different, but we use the generic equations, we focus on what we're left with, and there's only 3 possibilities. Okay. So question 11. We know it's an acid-base problem, but now then we count 1, 2, 3 things. So we know it's a reaction of a buffer. And we note that we have the strong base. So we know this time we're going to take our weak acid plus our strong base to make our conjugate base. And water. And so we do a start, react, left. This is getting pretty standard, I think, isn't it? In moles. Okay. And the same 3 things can potentially happen. We're going to be left with some of our weak acid and some of the weak base. This is all gone. We have a buffer. We do a buffer formula, Henderson-Hasselbalch. This is all used up. This is all used up. We're going to be left with a weak base. So we do a weak base KB problem. Or we're going to be left with some of this. And so we get its molarity, get its POH, and then get the pH. So once again, we're starting with different things. It looks a little bit different. But if we use the right equation, oh, and the other thing is, well, is this the A minus or is this the HA? Well, this has 3 protons. This has 4 protons. So that makes this our weak acid, our HA, and that makes this our weak base, the A minus. Okay. So one more example of this. Yeah, one more example of this. And so we know it's an acid-base problem. We've got 1, 2, 3 things present. So we know it's a reaction of a buffer. And we note that this is a strong base, so we're going to use the same equation. Okay. So the emphasis I put on this one is, again, you've probably not seen these chemical formulas, but as long as you can count protons, that's all you need to be able to do. We see this chemical formula has 5 plus 2, it has 7, whereas this chemical formula has 5 plus 3, it has 8. So because this one has 8, 1 extra 1, this one is going to be our weak acid. This one is going to be our weak base. And then we just do the same type of problem that we did right here. Start, reaction, left, and we take a look at what we're left with and go forward from there. All right. Okay. Anyone have any questions right now? I think that'll keep you busy this morning. Unmute all. Everybody's muted again.
Yeah, I muted myself because it
Okay.
was getting loud over here.
Okay.
I'm eating oatmeal. I didn't want you to hear it.
Okay. All right. All right. I understand. All right. So go ahead and have a go with what I've just provided you. And then if you run into additional questions, send them back to me. I think what I said before is if you just want to do a couple questions, send me your answers to those questions, see that you're doing those questions right, before you try to do everything and then find out you're doing the same mistake 10 different times. You don't have to send in the completed assignment all at once. You can send in a couple questions at a time. That's cool. And I'll get you feedback on those couple questions at a time. I think that might, if you're not at all totally confident, that might be the more efficient way then to do it versus doing all of them, making the same mistake on all of them, and having to redo all of them. Okay. So you just continue scanning them, taking a picture with your camera, whatever, and emailing them in to me, and I'll get back to you throughout the day and on over the weekend.
Do you know when when the recording of this?
I don't have another meeting until 10:30, so that's what I'll work on in between this meeting and the next meeting.
Okay, cool.
Is getting this recording up.
Perfect.
And then I'll send you the links. I'll send you the once I get that done, I'll send you the links to it as an announcement.
Okay, and then that'll be probably just in the file section of.
No, it's going to be in YouTube.
Oh, okay.
Yeah, Zoom puts things up in YouTube. So what I'll do is I'll send you a link to my my YouTube file, folder, whatever you want to call it. Mm-hmm.
Okay.
Yeah,
cool.
I think if I started uploading even all these videos, my my disk space would be over the limit they give me right now. So yeah.
Cool.
Yeah, so look for an announcement for me sometime today.
Okay, awesome.
Okay, great. All right, everybody. It's been nice again. Like I said, though, feel free to send me any questions that you want. I know it's going over the weekend, but like what I said before, I will check email regularly. Friday, Saturday, Sunday, get back to you as well on all that.
Good, Dr. Sila.
Mm-hmm. You doing okay, Heather?
I am, yeah.
You feel more comfortable about the problems?
Hopefully I'll get question B done today.
All right, good.
Thank you.
Oh, you're welcome, Heather. Okay.
All right.
I'm going to go ahead and stop the share, stop the meeting to Shelby, are you still there?
Yeah, I am.
Okay, you doing okay, Shelby?
Yeah.
Okay, you
yeah,
think
I'm
this
doing
will
fine.
help clear things up?
Yeah, I was just because I would find the pH with the negative log, and then I would subtract that answer by 14, and then it would mess with my acid. And yeah, I was just doing an extra step.
Yeah. Okay. We're making progress, folks. We're making progress because, like I said, this. The other thing, and I think I mentioned that before, I left a lot of material out of the end of chapter 16. If you look at my study guide for chapter 16, there's going to be a lot of stuff in the study guide near the end of it that is not included in this presentation and in the problem sets. You're not responsible for that. The study guide has an awful lot of calculations relating to what's called simultaneous equilibrii, calculations pertaining to qualitative analysis, you're not responsible for that. If it doesn't appear in the presentation that I've given you, but it appears in the study guide, you're not responsible for that portion of the study guide. So if you're making use of the study guide, so don't worry about that. And there may be 1 or 2 questions in the problem sets that I provided you outside of the homework one that you're not responsible for. Those are going to be like the simultaneous equations or the qualitative analysis type questions. So just blow by those. Don't worry about those. And if you're unsure of some question that you may come across, just copy paste that question, send it to me, and I will certainly inform you. Skip it, or this is one I want you to be able to do. So if you come across something you're not sure of, just send it to me and I'll let you know. Okay. All right, I'm going to stop share. I'm going to shut down and I'll start working on getting this up on YouTube so you can all view it later.
Okay.
All right. Bye-bye.
Thank you.
All right,
Bye-bye.
thanks. Bye.
Thank you.
So where is my... end?